Okay, almost done with the chapter. Got just a few more quick points to hit, okay? So the first one is a quick note on 1,2 diol formation. Okay. A diol is a compound that has two alcohols. If it's a 1,2 diol, they're on adjacent carbons. So for example, here's an example of a diol. So 1 carbon, 2 carbon there. Okay. If we react epoxides, we can form diols. Okay. So if we have an epoxide like this one that I'm writing here, and if I wanted to form a diol, so 2 alcohols, what should my nucleophile be when I open up the epoxide ring? It should be hydroxide. If it's hydroxide, okay, I'm not under acidic conditions, so it's going to be SN2 chemistry. The nucleophile will attack 1 carbon. If it's SN2, it's going to be backside. If it attacks 1 carbon from this way, the bond that breaks here in this group is going to be pushed the opposite. So I would get trans diols. So either like this, or I've got a mixture of this, and this, trans diols. Okay. To make the cis, we have to use a special reagent. Okay. To make cis, we use what's called osmium, so OS, tetroxide. Osmium tetroxide. Okay? Okay, and we react osmium tetroxide with an alkene, not an epoxide. Okay? To make a cis 1,2 diol, we react an alkene with osmium tetroxide. So let's look at that now. For example, cyclohexene. Okay. If I react it with osmium tetroxide, OSO4, okay, OSO4, and then I add in there some hydrogen peroxide, okay, and water. My final product will be a cis 1,2 diol. You can use wedges or dashes here. Okay, wedges or dashes. Cis. Okay. So keep this in mind. If you got to know the 2 ways. If you're asked to make a cis diol or a trans diol, or if you're giving that as part of a synthesis problem, it's important to know how to make both cis or trans. Okay, so we talked about alcohols, ethers, epoxides. We said all of them can do substitution chemistry, but amines cannot. Okay, so that's the question: why doesn't, or why won't, or why don't amines undergo substitution reactions? Okay. So the answer, to solve that problem with alcohols, to solve that problem with ethers and some epoxides, we protonate it. We activate those groups to make them better leaving groups. If we protonate an amine, it turns into our leaving group, it's still a poor leaving group. Okay? So that's why substitution doesn't happen. So even if we protonate, okay, even if we protonate the amine, it is still a poor leaving group. Okay, so let's look at an example. Butylamine. Okay. Hypothetically, I could say react it with HI to do a substitution reaction. So protonate the amine, iodide would attack to give me the substitution product plus ammonia, NH3, as my leaving group. This is a very poor leaving group. This prevents the reaction from happening. Okay? If you compare the pKa's of the conjugate acid of ammonia, ammonium, I think it's somewhere around 9 or 12. Okay? And the pKa of protonated water, hydronium, you're looking at -2 or something like that. So that means the conjugate base of hydronium water is much, much more stable than the conjugate base of ammonium, which is ammonia. Or you can just say ammonia is a stronger base than water, it's more reactive. The only things that we need to be concerned with about amines in this chapter is quaternary ammoniums. Okay? Quaternary ammoniums. So only if I spelled that right, quaternary ammonium hydroxide salts, okay, undergo E2 elimination. Okay, so what is a quaternary ammonium hydroxide salt? Ammonium is NH4 plus, right? Quaternary means 4 alkyl groups. So if instead of 4 hydrogens we have NR4 plus, R being methyl, ethyl, propyl, whatever, 4 of the same, 4 different ones, this is a quaternary ammonium species. Positive charge is going to be stabilized by forming a salt with something that's negatively charged. So a quaternary ammonium, a quaternary, man, I have to edit this video. A quaternary ammonium hydroxide salt would look like this. Okay, it would look like this. So let's look at a specific example now. Okay. I'm going to move it down. You probably can't see it too good on the screen. Okay, there's a quaternary ammonium salt. Nitrogen has 3 methyl groups, okay, and then this alkyl chain here. It'll undergo an E2 elimination reaction. So what's going to be my base? It's going to be the hydroxide. Okay, it's going to be the hydroxide. E2 elimination, we've got to find our beta hydrogens. Got to find our beta hydrogens. This is the alpha carbon. There's 3 here. And there's 2 here. Usually we try and form the most substituted, most stable double bond in an elimination reaction. Okay? Zaitsev rule. You deprotonate the beta hydrogen that's connected. You deprotonate from the beta carbon that has the fewest amount of beta hydrogens, 2 here and 3 here. So you would think that we would deprotonate here. But under what conditions did we talk about earlier in chapter 10, where you got the opposite, where you form the least stable product as the major product? When we used the porous leaving group, which was fluoride. Ammonia is a worse leaving group than fluoride, so it's going to react just the same. So our base will deprotonate, okay, here to give us the least stable alkene product than here. So it doesn't follow Zaitsev rule. We form our pi bond, and well, it's not ammonia in this case, I'm sorry. Just be trimethylamine would leave, and we will get this product. NCH3, 3. That's the leaving group. Okay. So NH3, or this amine species, is poor leaving group, like fluoride. Okay. It's a poor leaving group like fluoride. Okay. I hope the video is going fine, going good. If not, you gotta give me feedback. Okay, send me an email. Let me know, hey, I couldn't see this, or you're going too fast, or I can't understand it in this format. If that's the case, you gotta let me know so we can make it better or do something else. But now we're on the last part of chapter 11. Okay, last part on chapter 11. And it deals with thiols, so sulfur-containing compounds here. Thiols, sulfides, okay, which we also call thioethers. Thioethers, and sulfonium. Sulfonium species or sulfonium salts. Okay. All right. So recall that a thiol, just like an alcohol, except we got a sulfur atom instead of oxygen. Okay, sulfur instead of oxygen. That would be ethane thiol. All right. If we deprotonate this, we would form what's called a thiolate. A thiolate. Thiolates are excellent nucleophiles. Excellent nucleophiles. Okay. Excellent nucleophiles. Stronger. This thiolate is stronger than ethoxide. Okay. It's a stronger nucleophile than the oxygen-based version. Okay. We can do substitution chemistry with them. You can do substitution chemistry with them. For example, I take this thiolate, react it with an electrophile. What would be my product? What kind of reaction would this be? Primary alkyl bromide, okay, with a good nucleophile. It's SN2. If we wanted to put a solvent in here, we could put methanol. Okay, or maybe an aprotic solvent would be better. But it really doesn't matter here. The nucleophile will attack, backside attack, concerted reaction, attack the carbon, form a new sulfur-carbon bond, and get rid of the leaving group. All in one step. So if we write the product, we can start with sulfur. Okay. It had 1, 2, 3 carbons on it in the nucleophile. That didn't change. 1, 2, 3. It formed a new bond with this carbon, and there's 2 more carbons, part of that change. So add 3 carbons. 1, 2, 3. You're done. You can say plus Br minus. Okay? So the thiolate reacted to form a thioether. Okay? A thioether. This is an example of a sulfide or a thioether. Okay. Guess what? They're also good nucleophiles as well. They can do substitution chemistry too. So for example, CH3, CH2S, CH2, CH3. So here's a thioether. I can react it with the very same thing. Let me move it over a little bit. And do SN chemistry here as well. SN2 chemistry, excuse me. Nucleophile attacks the electrophile. The leaving group leaves. Okay, I form a new sulfur carbon bond. So there's 1, 2, and 2 carbons, and then a sulfur. So you can say CH3, CH2, sulfur. These are still there as well. And then I formed a new sulfur carbon bond. Okay. Sulfur was happy with 2 R groups on it. It now has 3. It lost a lone pair. It's a positive charge. There's a sulfonium. Okay, a sulfonium. Okay. Why are we interested in sulfoniums? Let's look at it. So what would happen here? What if I took a sulfonium okay, and I reacted it with methoxide? What would be my major product there? My major substitution product here. So now my sulfur-containing species is an electrophile instead of a nucleophile. Methoxide is my nucleophile. So the nucleophile is going to attack the electrophile. Be careful here. It looks like you would expect the nucleophile to directly attack the sulfur, form an oxygen-sulfur bond. That's not what's going to happen here, though. So if I did that, and under traditional SN2, reactions, nucleophile attacks electrophile, what would my leaving group be? It would be CH3 minus, okay, a methyl anion, which is very reactive. It's not a leaving group at all. So instead, what happens is the oxygen will attack a carbon and form an oxygen-carbon bond, causing this entire species here to be my leaving group. So it'll leave as a thioether, much better than methyl anion. So my substitution product would be dimethyl ether. Okay, nucleophile attacks that methyl group there, and then my leaving group would be the thioether. So the moral of the story is sulfoniums are good leaving groups. And that's it. That's it for chapter 11, okay?